Hi everyone, welcome back. Doing another lecture, new set of chapters. We are going to be combining everything we've learned about electric fields and magnetic fields together to discuss what they do. And electric fields and magnetic fields actually work together to create electromagnetic waves that we use for almost every single thing we do, right? Communication, we use electromagnetic waves for medical treatments. We use them to image our bodies, so they're really important. And we're going to talk about the electromagnetic spectrum and a little bit of physics behind how we describe electromagnetic waves. So light is just one example of an electromagnetic wave. We use light to see, right? So what is light? It's a good question. The answer was discovered by a physicist named James Clerk Maxwell. And we're going to be looking at the 4 equations that he put together to describe how electromagnetic waves move in space. So light is an electromagnetic wave. And what is a wave? A wave is a traveling disturbance. I don't know if you remember that definition from Physics 1 when you learned about mechanical waves. You may remember your professor shaking a string and you saw peaks and valleys appear on that string. And the displacement of the string from its equilibrium position was the disturbance, and it traveled along the string like a wave. And so electromagnetic waves are very similar. They're a disturbance in space. And that disturbance is a disturbance of the electromagnetic field amplitude. That is what is traveling through space. So a difference between an electromagnetic wave and a mechanical wave is that a mechanical wave requires a medium to transport the wave, like the string. Or if you make a splash in a pond, you see the ripples there, right? Those ripples wouldn't be there unless there was a pond or a body of water to make the splash in. But electromagnetic waves, they don't need anything to propagate, and they can actually propagate through vacuum, right? Vacuum is the absence of anything in the air, like no air, no molecules, right? It's nothingness. And electromagnetic waves can move very easily through that. So that's what makes them very interesting. And so what is an electromagnetic wave? Well, it involves what we've been learning about. It involves electric and magnetic fields that are oscillating. And the amplitude of the electromagnetic wave is, or I should say the amplitude of the electric and magnetic fields are what is being disturbed in space, and that is traveling through the space. So we're going to talk about a little bit of math. Well, first, I think before we get into the math, we're going to talk about the electromagnetic spectrum as a whole. So experiments have shown that in vacuum, right, which is the absence of any kind of materials or molecules or atoms, in vacuum, all electromagnetic waves propagate at the same speed, okay, because there's nothing there to slow them down, right? So they're all going to travel as fast as they possibly can. And the limits of that is the speed of light. So the speed of light is the fastest at which an electromagnetic wave can travel, and they're going to move the fastest in vacuum. So the speed of light is the speed at which all electromagnetic waves from one end of the spectrum to the next can travel at, and that value is 2.99 times 10 to the 8, and we'll use 3 times 10 to the 8 for our calculations. So while they do travel at the same speed, they will have different frequencies and wavelengths, and we will talk about that. You may remember the relationship between speed, frequency, and wavelength when we learned about mechanical waves in Physics 1, and that is the velocity of the wave equals the frequency times the wavelength. Sorry, that's my robot vacuum. And something must be stuck in his little mouth. So he'll turn off in a minute. So, right, this is the relationship between velocity, frequency, and wavelength. For mechanical waves, guess what? It's the exact same relationship for electromagnetic waves, okay? It's actually the relationship for any kind of wave. So that relationship for electromagnetic waves in vacuum, right? In vacuum is the speed of the wave, which is c, speed of light, equals the frequency times the wavelength. Okay, so this is true for all electromagnetic waves in vacuum. In the next chapter, you're going to see that when these electromagnetic waves move through some other material, this equation will be true, except c will be replaced with velocity, okay? But for now, we're talking strictly in vacuum. So the speed of every single electromagnetic wave will be the speed of light, c. So let's talk about the spectrum, right? So there's like a lot of types of electromagnetic waves. Light, which is maybe the most important one, because that's the one that we use to see, right? Our eyes were evolved to sense electromagnetic waves in a certain wavelength frequency range, okay? So it's very important to us to understand this spectrum of electromagnetic waves. Light is a very small part of the electromagnetic spectrum, visible light. It's right here, okay? And the wavelengths that our eyes have evolved to use as visual information is on the order of 10 to the minus 6 meters. But the way we usually write them is anywhere between 700 nanometers. So we usually describe it in terms of hundreds of nanometers, which is 10 to the minus 6 meters. Anywhere between like roughly 700 to 400 nanometers. Okay, so that's the wavelength range that our eyes have been, evolved to see and to interpret as visual information through the rods and the cones inside your eyeball. And so it's important. Let's look at waves below red, or maybe I should say above red. Depends on if you're talking about wavelength or frequency, because you can see they're inversely proportional, right? The largest wavelengths, 10 to the 3, have the smallest frequencies, 10 to the 6. Smallest wavelengths, 10 to the minus 13 size, have the largest frequency, okay? So lambda and F are inversely proportional. And why is that? Because F times lambda must equal always the speed of light when in vacuum, right? So the larger the wavelength, the smaller the frequency must be. So anyway, if we're looking on the left side, which is small frequency, big wavelength, we're going to have infrared, okay? Infrared below red. Infrared is the wavelength that heat gives off. So if you've ever put on like night vision goggles, or maybe you've heard of them, the way night vision works is you have a device that is able to sense infrared radiation or infrared electromagnetic waves. And heat gives off infrared radiation. Microwaves, important microwaves, we use to communicate. We also use them in a microwave, okay, to heat up our food. But we use them. Wi-Fi is in the microwave range. 5G is in the microwave range, right? That we use, cell phone towers communicate. And then we have radio waves, which is a very big band. So we call these bands. These are bands of frequency. This is a band, right? Encompasses a bunch of different frequencies, a bunch of different wavelengths. We call those bands. So now let's look at the other side of visible light. UV, very important to know about, because UV can be very dangerous for biological creatures, right? UV is very damaging and can cause cancer. It's important to understand wavelength radiation in the wavelengths in the ultraviolet region. So our sun, why it's so important to us as beings on this earth is that the sun puts out a ton of ultraviolet radiation. And we're so lucky that we live on this planet that has developed an atmosphere that blocks most of the ultraviolet radiation. Although lately, more and more of it has been penetrating through for reasons that are not fully understood. So it's really important to protect yourself against ultraviolet radiation. And you can see it's ultraviolet right above violet. So it's right next to violet, it's at the edge of what we're able to detect with our eyes. There's many biological creatures that actually can detect ultraviolet radiation. And those creatures, interestingly enough, they are in very dark places, because if they were to walk out here on land with us and you were able, let's just say you and me were able to see ultraviolet radiation with our eyes, we would just see brightness, because there is so much ultraviolet radiation coming from the sun that it would just overwhelm our eyes and we wouldn't be able to see anything. Everything would be too bright. And so that's kind of the reason why our eyes don't detect ultraviolet radiation, and why our eyes started to detect right at that edge, around 400 nanometers. So let's talk about the animals that do. This is pretty interesting. So snakes can actually detect infrared, right? Heat signatures. Some fish, right? So let's talk about fish living deep in the water where light does not penetrate. However, ultraviolet light does penetrate farther in water, and fish are able to detect it to aid them in, seeing what they need to see. And so, for example, this is a perfect example. Here we have two fish. They look identical to us, right? They are yellow fish. They both have, like a little fin up here shape, right? They look identical. They both have a little dot here, okay? We have difficulty telling these fish apart, but these two fish can see in ultraviolet light, and they are able to tell the difference between the species. Because they can see in ultraviolet light, they can see the pattern of their scales and tell that one fish is of their same species and the other fish may not be. Okay, so they evolved this ability because down in the ocean, deep in the ocean, visible light does not penetrate very far. It ends up getting stopped by all the water molecules, but ultraviolet light is able to pass through easier and reach their eyes. And it's also a little bit filtered because if it was too bright, it would be difficult to distinguish, the features. So really, really interesting, ultraviolet light, being near visible light is very interesting because of how biology interacts with it. It's the most prominent wavelength that comes from our sun, so it's very important biologically, and it can also be dangerous, right, as we know. So now that we kind of talked about the fun, interesting stuff, let's get into the nitty-gritty. Let's describe electromagnetic waves mathematically. And the way we do that is we describe electromagnetic waves using a sinusoidal wave that is a plane wave. Okay, and so we'll dive into what that means. So we know that a wave is a disturbance that propagates through a medium. Electromagnetic waves don't need a medium to propagate, but they can propagate through a medium. And so what is that disturbance? That disturbance is a disturbance in the electric field and the magnetic field in that particular area. So you can see the disturbance would be this peak in the electric field and this peak in the magnetic field from its equilibrium position. So these peaks we model as a sine wave, right? Starting from at zero and then oscillating in a sinusoidal pattern. And you can see that the E field magnitude max and the B field max magnitude occur at the exact same place. So we are looking at two sine waves that follow the same pattern, one for the E field and one for the B field. And the amplitude we're going to call of those waves E naught and B naught. So these fields, these waves, are transverse. And so what that means is that they are perpendicular to each other at all times, right? You can see that the E field is in the y-axis, the B field is in the z-axis, and they are also perpendicular to the direction of their motion, which is in the x-axis. So this is a transverse wave. Okay, the two fields are perpendicular to each other, and both of those two fields are perpendicular to the direction that they move. And they have the same wavelength, which is what I explained before, right? Their peaks occur at the same time, their zeros occur at the same time or place, and so therefore E and B have the exact same wavelength. So here is a picture and an equation or a set of equations that we use to describe the magnitudes of the E field and the B field. We're going to use cosine functions. It's really arbitrary if you choose to use sine or cosine. And that's because we have this kind of phase addition at the end, which will allow us to switch between sine and cosine. For example, cosine, and if this was a 90 degree, well, that would just simply turn it into a sine function. So just by convention, we choose to use a cosine first, cosine function to describe it. And so this is a sinusoidal wave, right? There's two sinusoidal waves. What makes it a plane wave? So let me explain this plane wave aspect. What we're looking at right here is just one singular wave, right? But when something emits electromagnetic radiation, it doesn't just put out one wave. It puts out an infinite number of waves that are taking up all the space around it. And so if we consider more than one wave, let's just, I know it's not a million or infinite, let's just consider 6 waves. And if we isolate up a plane, okay, that all these waves are penetrating, for example, a plane in the YZ, okay, then the plane part comes from the fact that that electromagnetic wave everywhere in that plane has the same amplitude, right? All the little electromagnetic waves that penetrate that plane are going to have the same E field, and then they're going to have the same B field everywhere, okay? So the magnitude of those E fields and B fields are constant in the plane. So that's what a plane wave is. The magnitudes of E and the magnitudes of B are constant everywhere in the plane. That's the meaning of a plane wave. And so here, if we were to investigate and cut out a plane here at the 0, well, then everywhere in that plane, the E field would be 0 and the B field would be 0, okay? And if we were to cut out a plane right here, okay, then you can see the B field, the E field pointing down and the B field pointing to the right. Well, everywhere they would have that same magnitude. Now, I'm not saying that E and B are equal. I'm saying that all the E's are equal and all the B's are equal. But E and B are related to each other in this way. Okay, I'll spare you the derivation of this equation. I'm just going to show it to you. The E field magnitude and the B field magnitude are related to each other through the speed of light. So the B field is equal to the E field over C, and then we can express it in terms of the E field. Well, the E field is equal to CB, okay? So that's always true for electromagnetic sinusoidal plane waves, okay? And so let's, we looked at the magnitude. Let's examine what's in the argument of the cosine function. So you may not have seen K in a while, right? K came up when we talked about mechanical waves in physics 1. K is the angular wave number, okay? And it's related to the wavelength. K is equal to 2 pi over lambda, okay? And then we have omega, which you do remember from the previous chapters. Omega is the angular frequency, which is simply 2 pi times the regular frequency. And then phi is that phase angle, right, which tells us what is are we dealing with a sine or a cosine function, basically? At what point, in other words, at what point in the oscillation cycle are we at x equals 0 when we're starting the wave, or when we're starting measuring the wave? Okay, we're not going to be dealing much with the phase angle, so I don't want you to worry about it too much. So now the magnitude of E field and the magnitude of the B field, you can see that they're gonna depend on both position, so the location that you are on the X or Y or Z axis, and the time. So these sine waves, I mean, kind of have like two natures to them, right? You can look at the sine wave, and because we can't see both space changing and time changing at the same time, we need to kind of hold one of those variables constant and vary the other, and vice versa, in order to see the complete wave, right? So for example, what I'm saying is that, look at this picture here. This picture is showing us a whole span of x's, right? So that must mean that we're looking at it at one snapshot in time. So this wave is occurring, let's say at t equals, 1 second or something like that, right? At one moment in time, I took a picture. Well, we could also express the wave in the same way, but we can look at the time dependence of the wave at one location. And you're going to get the same looking, you're going to get the same looking graph pretty much, right? So if instead we vary time, then we vary position along the x-axis, well, you're also going to get a cosine function. So I'm just wanting to explain to you, right, that there's two variables here that can change, but when we look at a picture of a sine wave, we are not able to see both at the same time. So we hold one variable constant and change the other. So this is going to be the position dependence at one moment in time, and this one would be the time dependence at one position, let's say x equals 0. And they're going to look the same, right, because they're both cosine functions. Now they're going to have a different factor here, right? And so, like, for example, the wavelength in this graph, if we're holding t constant, if we're holding x constant, the wavelength would be related to this factor right here. And I know I'm saying wavelength, right? I'm speaking generally about a sinusoidal function. I'm not saying that's lambda, but this distance here on the sine wave is going to be related to this parameter. Whereas if I am looking at this wave right here, and I'm keeping t constant, then this wavelength here is going to be related to k, okay? And maybe instead of using the word wavelength, I should use the distance between peaks. So I believe there's one or two problems in your homework that kind of dive into that concept. So I just wanted to make you aware, to think about that. So let's do an example that'll just help us kind of get familiar with the terminology and some of these equations that we've been looking at. So let's say we have a radio station that broadcasts at a frequency of 98.7 megahertz. Okay, so 1 megahertz is 10 to the 6 hertz. So F is 98.7 times 10 to the 6 hertz. And that wave reaches the radio in your car, and the electric field amplitude of that wave is given as 6 times 10 to the minus 2 voltmeters. can we calculate the wavelength of the wave and the amplitude of the magnetic field? So we want the wavelength and then the amplitude of the B field. Okay, so what's a little bit unspoken about this problem is we're assuming that this wave is in vacuum. So we know the speed of it off the bat. The speed of it is the speed of light. And we know that the speed of the wave is equal to the frequency of the wave times its wavelength. So since we're given the frequency and we're given the speed that the wave is traveling, we can very easily find out the wavelength. So it's going to be C over F, which is 3 times 10 to the 8 meters per second over 98.7 times 10 to the 6 hertz. And that gives us, get my calculator up. A wavelength of roughly 3 meters. Okay, 3.04 meters. So what about the amplitude of the B field? Well, you might remember the relationship between the B field and E field amplitude. So B, sometimes I get it, yeah, B equals E naught over C. Sometimes I get them switched up. So we can easily calculate that. And we get a very little B field, of 2 times 10 to the minus 10 Tesla, okay? And so this was a pretty straightforward example, but what I want to comment on that you should, that this example is also illustrating is the relative sizes of the fields. So the E field will always be much bigger than the B field, okay? The E field will always be much, much larger. Look, we have a 10 to the minus 2 versus a 10 to the minus 10, right? So the E field will always be much larger than the B field. That's always true. And the other illustration here is that, and I mentioned it before, right? If the speed is constant, then, and the wavelength is small, well, then the frequency should be big, right? And that's what we see here. We see a large frequency, roughly 10 to the 6, and then a small wavelength, 10 to the 1, okay? So those relationships, kind of like having a good idea of the sizes of these things is gonna help you check your work, because it's really easy to make a calculator mistake here, right? To put a -6 when there should be a +6 in the exponent. It's really easy, and if you don't have like a good intuition about the sizes, it'll be hard to check your work. So, and you don't want to, lose points making a silly mistake like that. So let's look at this. Got the concept, electromagnetic wave speed. So let's say we have 4 electromagnetic waves and they're in vacuum. Okay, I highlighted that. They're in vacuum and they have different frequencies. Which of these waves are going to propagate at the fastest speed? So which will move the fastest? So we have, let's see, like a 10 to the 6, 10 to the 7, 10 to the 11, 10 to the 8. So we have some high frequencies here. What speed are they going to be moving at? Let's take a look at the equation that we have for the speed of the wave. Hold on a minute. The speed of the wave is a constant, right? Because it's in vacuum. The speed of the wave is constant. 3 times 10 to the 8. So guess what? They all move at the same speed. Kind of one of those trick Trick got the concepts, right? Right? They all move at c. C is a number. C is not a variable, right? C is a number. 3 times 10 to the 8. It's not a variable. It doesn't change. Okay? So just to review this section, we discussed electromagnetic waves, right? Some really cool properties. They're super useful for us. They're very important to us and other creatures, right? We communicate with electromagnetic waves instantly, right? We can call someone in Thailand and make sure they're okay after the earthquake. We can use electromagnetic waves to see the world around us, right? Our eyes have evolved to interpret wavelengths between 700 nanometers and 400 nanometers. And these waves can be mathematically described as sinusoidal functions that vary both in time and space. And the directions of the E field and the B field and the velocity direction are all perpendicular. So those are all the kind of key points of this section. So now we're going to get kind of real physics-y, okay? We're going to talk about Maxwell's equations, and we're going to be discussing a lot of the big equations that we used pretty much since like the second or third day of class to just recently. And they're all going to be kind of combined together, and that set of equations are described as Maxwell's equations and describe the way that electromagnetic waves move in space. And they basically tell us why electromagnetic waves exist. So you might remember, right, Ampere's law, Faraday's law, Gauss's law, right? All of these guys were not working together. They were all working independently, doing experiments, discovering these laws. And James Clerk Maxwell, he took all those results from those physicists and mathematicians, and he was able to look at them all and see the connection between them and see the symmetry and see what they all meant. He connected them all together and even kind of modified one a little bit. He basically took like all these experiments from different people over different years and forged them into a unified theory that describes electromagnetic waves. And this set of equations is called Maxwell's equations. There's 4 of them, and they describe anything to do with electromagnetic phenomenon, okay? So we're going to look at these equations, all right? We're going to look at them one by one, and they're going to look familiar. You may recall Gauss's law, right? That was kind of like the first tricky conceptual law that I introduced to you in this course. Gauss's law states that the electric flux through any closed surface is going to be equal to the charge inside that surface divided by the constant epsilon naught, right? And so Gauss's law tells us that, you know, the electric fields that penetrate some surface, if we can calculate the flux, right? So if we can calculate the flux by looking at all these field lines and how they penetrate the area, well, then we can know what charge is inside. Or if we know what charge is inside, and we know the area of the surface, and we can find out the E field, right? It kind of went both ways. So Gauss's law is the first of Maxwell's equations. And the second is Gauss's law again, but it's for magnetic fields. And we didn't really talk too much specifically about Gauss's law for magnetic fields, but you may recall this. How we did describe it was, well, first let's look at it, right? Gauss's law for magnetic fields states that the magnetic flux through any closed surface is equal to 0. And the way that we described that when I first brought up magnetism to you guys is I said, hey, remember north and south poles can never be separated, right? Even if you cut it with a knife infinite number of times, they will spontaneously, each piece will turn into a north and a south pole, right? So It doesn't matter how many times you cut those pieces, they will spontaneously break into a north and a south pole. And so what does that have to do with Gauss's law of magnetic fields? Well, if I enclose a north and a south pole in a surface, the magnetic field lines come out of the North Pole, right? And go into the South Pole. Well, guess what? The flux will always be zero, right? Through that surface, because you have just as many outgoing vectors as you have incoming vectors, and they will cancel each other out. So no matter what, the flux through a surface that surrounds any kind of magnet is going to be zero, okay? And that is true even if we're not talking about a magnet, we're talking about a current carrying wire, okay? And that's what this picture up here shows. So you can see that if we enclose any portion of a current carrying wire, the magnetic field lines will come out and go in, come out and go in, come out and go in, come out and go in. They will always, the flux will always add up to zero, okay? And so the reason is because we don't have isolated north and south poles, right? They don't exist. We don't have, we don't have the plus and the minus charge behavior like we do for electric fields, right? We don't have poles that can be separated. In magnetism, the north and the south pole, the source of the B field and the sink of the B field can never be separated. And so if you enclose anything that is a source of a magnetic field in a surface, the flux will always equal to zero, because the B field lines coming out will equal the B field lines coming in. Okay, so that's Gauss's law for magnetic fields. That's the second of Maxwell's equations. Now what this slide is telling us, there's a little bit of a derivation. I'm just going to kind of get to the point of this slide. Okay, what Gauss's laws, the two Gauss's laws, tell us is that the type of electromagnetic wave that describes electromagnetic radiation must be a transverse wave. Okay, which I mentioned before. What is a transverse wave? E perpendicular to B, perpendicular to the direction of propagation, right? That's a transverse wave. And so those two Gauss's law tells us that the wave must be a transverse wave, and versus a longitudinal wave. So longitudinal waves cannot describe Maxwell's equations. They're not a good fit. If you want to know more about that, you can kind of look, through the bubbles of these two figures. But I'm going to spare you that derivation. And if you can just accept the fact that Gauss's laws tells us that the wave must be a transverse wave, then we're good. You're good with that. So now let's look at the third Gauss's law. Before we get to it, we're going to kind of have to modify what we know. Let's look at Faraday's law, right? It should be still fresh in your head, Faraday's law. A voltage or an EMF is generated when a magnetic flux changes with time. So we need to express this voltage in terms of an electric field because Maxwell's equations describe electric fields and magnetic fields. So we can turn this voltage into an electric field. You may recall that a voltage is equal to an electric field times the distance over which we're measuring that voltage, right? In other words, an electric field is a voltage divided by a distance, and that may be more clear to you because remember there's a unit we can use for electric field, which is a volt over a meter. So if a voltage, which is an EMF, is equal to ED, we can kind of substitute ED right here, okay? And what that tells us is that an electric field, I'll go to that image in a minute, an electric field over a distance is going to give us a change in flux, okay? Or we can say that the other way around. The change in flux, magnetic flux, is going to produce an electric field, right? Because the change in magnetic flux produced a voltage for us. And a voltage is simply an electric field times a distance. And so we have this circulation thing again, which you may have seen with Ampere's law, right? All this left-hand side is telling us is that if we add up all the E fields that exist in this circular direction, right? Because in order to produce a voltage in a circular direction, the E fields must also be circular. So if we add up each E field over that small bit of distance, okay, we add up all those multiplied by each other, right? E times delta L, E times delta L. If we add them all up, what we're going to get is simply the magnitude of the E field times the circumference of that circle. Okay, so now that's for like a circular shape. If we are, right, because it's all the E fields parallel to delta L. Now let's say if we have like a square loop and the E field is going like this, well then the sigma E parallel delta L, right, this circulation will equal this delta L plus this delta L, right? Not these sides, because these are perpendicular to E, not parallel to E. So what we're doing here, the circulation, is basically adding up all the E fields multiplied by the distances that are parallel to the E field, okay? And because the E field is constant, you can kind of pull it out of the summation, and this circulation simply becomes E times all the distances that are perpendicular or that are parallel to E. And if that is a circle, that becomes 2 pi r. If that is a square, that of side length d, that becomes 2d. Okay, right? Because you're only going to be adding up the sides that are parallel to E. And there's only going to be 2 sides parallel to E at any moment in time. Okay, so mathematically, it looks crazy, but if you understand the concept behind this, it's an easy math. If it's a circle, the distance, delta L, all the delta L's added together will be the circumference of the circle. And if it's a square, it'll just be 2 sides, because E field will always either point in this direction or in this direction, right? So only 2 sides will be added up. So the electric field is produced by a changing magnetic flux. And that's kind of like part of the piece explaining why electromagnetic fields propagate through space, right? Because a changing magnetic field with time is going to make a new E field. And then that E field should change in time. And what does it do? Does it produce a magnetic field? Yes, it does. So that's going to be the second part, but we'll get to that. Let me kind of help illustrate this equation here, okay, with this figure, because we're going to be looking at this figure a lot. So I'm going to look at this figure and fully understand it, because it's going to come up in exams and in homework questions, okay? So look at this figure. We just have a magnet. These are the poles of a magnet, right? Here's the south pole. Here's the north pole. The B field goes from north to south, right? Okay. If we place a circular piece of wire in that B field and we change the magnitude of the B field, this should still be fresh in your mind from the exam, right? And let's say that we increase the magnitude of the B field. Well, then a B loop will be produced opposite to B, and it will create an EMF in the clockwise direction if you're viewing it from above, right? So that's an I. And we know that the EMF is created in that wire, right? But what if we take away the wire and keep clicking on the wrong thing, right? We're looking at this situation. What if we take away the wire and we increase the B field? Does nothing happen? No, right? Something still has to happen. Just because the wire is gone doesn't mean that what generated that voltage disappears. Because what generated that voltage was an electric field, right? Electric fields create a force on particles and getting them to move, right? Force is equal to QE, right? Force on a particle due to an electric field is equal to QE. So if there's an electric field present, then there will be a force, and there's charges present, then there'll be a force moving those charges. But if there is no charge there, there's still an electric field, okay? There's still an electric field there, and that's why we convert Faraday's law into this expression, because whether or not there's an object there, the electric field is still there, because we know that electric fields and magnetic fields can exist in vacuum, right? They can exist in nothingness. So I hope that helped you understand why we modified Faraday's law and how we did, right? So the left-hand side of Faraday's law now becomes the sum of all the electric fields parallel to the lengths, which we call the circulation, and that's simply adding up all the electric field magnitudes, multiplying it by that distance. So let's do an example that illustrates this. Okay, so here's that figure again, right? And we are going to be looking at situation B where we don't have a wire. So we're going to look right here. And it looks like we are starting with a magnetic field that is 1.5 Tesla, and it decreases to 0, okay? The question is, over some amount of time t, where t can equal 10 or t can equal 0.1 seconds. The question is, what's the magnitude of the electric field around a loop of 3.5 centimeters, right? Not a physical loop, but just a loop that we have traced out in space, right? Because there's no wire there. It's just, we're just kind of like, what's the electric field around this circle, okay? And that's what we're going to figure out. So we're going to use our new expression for Faraday's law. And so the way that we're going to attack the left-hand side is we're going to realize that the electric field magnitude is going to be the same at every point on this loop. And that's always going to be true for everything that we do. So we can pull that electric field out of the summation, and all we're doing now is adding up all the delta L's, which is simply going to give us the circumference of the loop, which is pi d, right? Because we're given it in diameter, so that's simply pi d, right? The circumference is 2 pi r or pi d, right? And then that is going to equal our right-hand side, which is the change in flux with time. So now let's tackle the right-hand side for part A. Right, part A is that the change in time is 10 seconds. And our change in flux is B final times the area minus B initial times the area, right? Because delta is always final minus initial, and flux is BA. And, well, it's BA cosine theta, but B and A are parallel, so cosine of 0 becomes 1. So I just dropped that off. And so our final B is 0, right? Because we're decreasing. And our initial B is 1.5 Tesla. And our area is the area of the 3.5 centimeter loop. So that's pi times 0.035 meters squared. And that is going to give us that is going to give us a flux of 0.0058 Webers, right, which is a Tesla meter squared, and negative. It's negative. We asked for the magnitude. We're asked for the magnitude, so we can actually drop off the negative, right? It wants the magnitude, so I can just drop the magnitude off, and I'll write that mathematically like this. Okay. So there we go. We'll make it sound. Mathematically sound. So there's our Weber. So there's our delta phi. There's our delta t. So now we're ready to put together the right-hand side of the equation. So let's rewrite the left-hand side. And the right-hand side, oh yeah, we're dealing with magnitude. So we're going to just drop off the negative, right? And so our delta phi b is 0.0058 Webers. And then our delta t is 10 seconds. And so we're solving for E. I'm going to go ahead and solve for E before plugging everything in. So E is going to be equal to 0.0058 Webers over 10 seconds divided by pi times the diameter. Oops, looks like I just caught myself in an error, right? I used the diameter here. Maybe you caught that too. This is not right. The area is not pi d squared, it's pi r squared. So I need to put the radius there. You might have caught me, maybe you didn't, but that's okay. 0.0175 meters squared. So now let me recalculate the flux here. 0.0175. And so the flux becomes, there we go, the flux becomes 0.00144. Okay. All right. Okay, now we're back. So now let's calculate 0.00144 divided by 10 times pi times 0.035. And we get an electric field magnitude of voltmeters. So that is, if we move this 1, 2, 3, 1.31 times 10 to the minus 3 voltmeters. So, and that's a good, that number makes sense. It's on the order of the last problem that we did, which gave us an E field of 10 to the minus 2. So it's not like an absurdly small E field, right? That would lead us to believe maybe we made an algebra mistake. So let's see what happens to the E field if we were to change the field a lot faster, right? If we were to change the magnetic field from 1.5 Tesla to 0 Tesla in 0.1 seconds, okay? So we can actually pick up this equation right here. We can start from here without having to reinvent the wheel, if you know what I mean, right? Because all we're doing is changing the time. So if we start right there, and we're going to change the time now to 0.1 second. Well, what does that do? Look, if we divide by a decimal here, that's going to increase the rate, right? That's going to increase the rate. So we should expect the E field to increase as well. So the faster that you change the flux, the larger the amplitude of the E field. Think back to the electromagnetic spectrum, right? Where we had a frequency really big, we should have a big E field, right? And I don't know if you know too much yet about radiation, those of you that are going into the medical field, but high frequency radiation is very dangerous, right? And because now we know, because the amplitude of the E field and the B field are going to be really big. Okay, so that's just something I'm going to just bring up, right? That's kind of what this example is illustrating. So we're changing now the B field at a more rapid pace, and that's going to give us a bigger E field. So let's see how much bigger it's going to be. So, okay, 144 Webers over 1 second divided by pi d, which was pi times 0.035, right? Diameter, not radius. And so I'm just going to, so we get 0.131 voltmeters, which if we compare that to the 10 to the minus 3, that's 131 times 10 to the minus 3 voltmeters, right? So we went up basically 100 times, right? It got 100 times faster. So, the rate of, the time difference got 100 times faster, and the E field got 100 times larger. Okay? So, it's an interesting example. And, right, the faster the frequency, the larger the amplitude of the radiation is kind of the concept behind this. And the other important concept behind this example is just knowing how to use the left-hand side, the circulation. So that was the third, right? So where were we at? That was number 3. That was Maxwell's law number 3. We're going to find Maxwell's law number 4, the last one, and it's going to have to deal with Ampere's law. Okay? So what we just saw by modifying Faraday's law was that a changing magnetic flux produces an electric field. Well, guess what? The opposite should be true, right? A changing electric field should create a magnetic field. Well, all we have to work with so far that we've learned is this. So how are we going to figure out how this is going to connect to electric fields? So let's remind ourselves what Ampere's law states. Ampere's law states that the circulation of a magnetic field is going to equal a constant mu naught times whatever the current is that's going through that loop. And we use that to figure out how to find the magnitude of the B field due to a current, right? And I spared you the derivation of that, but basically this equation gave us B equals mu naught I over 2 pi d, right? That's basically what Ampere's law gave us. But you can see that it's missing a piece. Something's missing here, okay? Something is missing because we don't have any relation to an electric field, right? And because we know that magnetic fields and electric fields can move through vacuum, and there are no currents in vacuum, right? Because in order to have a current, you need to have particles that are moving, positively charged particles that are moving. So we need to figure out how to incorporate the E field here. And let's do a little thought experiment. So we know that when we have a current carrying wire, a B field's created in a circular pattern around that wire. Well, what if I cut that wire and I kind of insert some plates? I insert a plate here, okay? What happens, is there a B field now? Well, we do know that these plates are a capacitor. They form a capacitor, and that there are electric fields between capacitor plates, right? So electric fields exist even if there is no wire there. And electric fields, if they're changing in magnitude, will create a magnetic field. So although there is no current in between the plates, there is still going to be a magnetic field created. And that's because the electric field is changing with time in between the plates. So in other words, there are two ways we can create a magnetic field. We can create a magnetic field by passing current through a wire. And then the other way we can create a magnetic field is by changing the electric flux. And so there's the symmetry, right? We knew a changing magnetic flux creates an electric field. Well, guess what? The opposite must be true. A changing electric flux also creates a magnetic field. So that's the missing piece to the fourth Maxwell equation that we're building. Okay, that's the missing piece. And so that's what Maxwell did. He said, wait a minute, we're missing something here, right? We have to complete the symmetry. It's not just changing magnetic fields create electric fields. There has to be symmetry here. Changing electric fields must create a magnetic field as well. And so there's the fourth Maxwell equation. It's called the Maxwell-Ampere law because Maxwell added a little bit to it. He added this bit, which states that a changing electric flux can also create a magnetic field, okay? And so let's kind of practice using this equation with this example. So we're going to have that figure again, and we are going to pass a current through a capacitor, right? We know electric fields exist between plates of a capacitor. And those, let's say the plates are 5 centimeters in diameter. So that's the diameter of these plates. And the electric field between the plates we're given, it has a magnitude of, it increases by 8 times 10 to the 5 in 1 second, okay? So this piece of information increases by, that's already giving us like the delta E, right? That's telling us that the delta E is 8 times 10 to the 5. Do you agree with that? And then our delta T is 1 second. And that induces a magnetic field. What is the magnitude of that magnetic field around a loop that's 3.5 centimeters in diameter? Okay, so we're gonna place a loop. It's not a real loop. It's not a current carrying wire or anything. It's almost like a Gaussian surface, right? It's called an Amperian loop, and it's just a fictitious loop where we're gonna measure the field around that loop. So let's use the Maxwell-Ampere law, and let's kind of break it down. So the left-hand side, we're solving for the B field. And the B field is going to be constant. So the B field and the E field, whenever we do a circulation, will always be constant. So we can take the B field out of the summation, and we're just adding up all the delta L's. And so this side here, this is going to be the circumference. But the circumference of what? It's going to be the circumference of the loop that we want to know the magnetic field around. Okay, and if you read the question, we want to know the magnetic field around a 3.5 centimeter diameter loop. So guess what? That's going to be the 3.5 centimeter diameter loop. So that's going to be pi. I'll go ahead and write that 3.5. Okay. That's what the left-hand side, this is the diameter of the loop that we want to know the field. What's the right-hand side? Mu naught times the current through the loop. So let's look at this loop. Here it is, the orange loop. Is there a current through the loop? No, right? There is no current in here. There's no current. The current is over here, right? Feeding the plate and then coming out of the plate. There is no current in the space between the plates of the capacitor, right? There's no current there. There's no wire there, right? It's space. It's empty space. So the current through will be 0. There is no current there. And the second term is going to be the change in flux with respect to time. So let's go ahead and write that out. The change in flux, that's going to be delta phi over delta t. I'll just leave this here. So what is the change in flux? The change in flux is the final electric field times the area minus the initial electric field times the area over delta T. Well, the area is constant, right? The area is not changing with time, so that can come out. And we have EF minus EI over delta T. And so I think we were given EF minus EI, right? That's a delta. That's delta E. That's this guy right up here. So that's 8 times 10 to the 5. And then delta T was 1. So, and then the area is going to be the area of what? The area of what? Let me write this out and we'll talk about the area of what. The area that the flux is changing through, right? And the area that the flux is changing through is the area through the loop that we want to know the B field. So any E field outside of that is not contributing to the B field, right? So the area here is the area of that 3.5 centimeter diameter loop, which is going to be pi. I didn't leave enough room here. Pi r squared, right? Not d. So there we go. So now we have everything we need to find B. We have a lot of stuff to put in the calculator. Maybe something will cancel, right? I'm not gonna plug in everything yet. And then maybe I can get some stuff to cancel and I can type in less in the calculator. So my pi times 0.035 comes down. Okay, my pi's go away, so that's one less thing I have to worry about. I think that's all that cancels. I mean, the R's kind of cancel and the D, right? Like, if I had written this as D over 2 and this is D, I would cancel those, right? But I already wrote them as numbers, so I'm just going to leave it for now. But just for your own purposes, if you are redoing this problem when you're studying for the exam, you could write everything algebraically first, and you would get some stuff that cancels, and you can get an equation, and that you can plug in your calculator very easily, okay? So that'll be my hint to you. So we're not going to cancel it now just because I don't have anything written algebraically yet. It's all numbers. So let's go ahead and type everything in. So mu naught is 4 pi times 10 to the minus 7. And epsilon naught is 8.85 times 10 to the minus 12. And then we have the diameter, or the radius squared. Then we have 8.00 times 75. And then all of that is divided by 0.035 squared. Okay, and we get a small number, which, remember, when we were talking about magnetic field magnitudes, we expect them to be much smaller than electric field magnitudes. So what I got from my calculations is 2.22 times 10 to the minus 12 Tesla. And to me, that number, you know, the previous number we got from the last example was like 10 to the minus 10 Tesla, so it makes sense. I'm pretty confident in my calculations. I think that's a good number, as long as I typed in everything correctly. So that's the magnetic field that's created by the change in electric field. So they're small. The magnetic fields are small. And go over these examples, 22.3 and 22.2. And then there's, I believe, a homework problem similar to these two. These are very good examples, okay? If I were to test on manipulating Maxwell's laws, right? This is the type of question that I would ask. So let's put all the equations together and let's look at them. Let's admire their symmetry, right? Physicists love Maxwell's equations because of the symmetry behind them, right? So we have the two Gauss's laws, okay, that describe how the flux of the E fields and the B fields through a surface and are what they are, the fluxes, right? And what those two Gauss's laws told us is what type of electromagnetic wave works and is solved by these equations, right? And only transverse electromagnetic waves can be electromagnetic waves. What the next set of laws, and you can kind of think of them as the Faraday's laws, one's the Faraday's law and one's the Ampere-Maxwell law, right? What they tell us is how the wave propagates, right? How is this wave moving through space, right? How is the light from a distant star that is thousands of light years away, how is that light eventually reaching us? I mean, it has to travel a very long way to get to us. What is keeping it going? And so what's keeping that electromagnetic wave going and going and going is the fact that a changing magnetic field through an area creates an electric field, and that changing electric field creates a magnetic field, and that cycle continues over and over and over, okay? That is why we can see stars from so far away, because that light makes it all the way to us from another planet or from another star, right? And that's why we can see stars better than planets, because planets don't emit light, right? They're not like a big ball of gas that is like just a huge, crazy, how the sun is, right? You've seen pictures of the sun. It's a lava ball, right? It's just emitting radiation left and right because it's very, very hot. Planets are not. We wouldn't be living on a planet if it was a ball of radiation, okay? Planets are like rocks, and rocks don't emit radiation. So that's why we don't see planets, but stars emit this radiation, and they emit so much, and it travels, and it can just make its way all the way here because the electric field constantly produces a magnetic field, and that cycle goes on and on and on. Okay, so that's what Maxwell's laws tells us, and that's what they told Maxwell, and why he was so excited, and and why physicists are so excited about it. So we can modify, because we have been talking about electromagnetic waves and vacuum, we can modify the fourth Maxwell equation to not include currents, right? Because currents don't exist in vacuum, right? Currents are positive charges moving. So by definition, a vacuum is an absence of atoms, right? So there aren't going to be any charges around. So we would get rid of that term and simply just have the Maxwell part of the Maxwell-Ampere law, okay? Which is just the change in flux. So if you see the equation written that way, now you know why. It's because we're talking about them in vacuum. So another interesting aspect of Faraday's law and the Maxwell-Ampere law that we didn't talk about quite yet is you can use them to find this relationship. Okay, I'm going to spare you the derivation of that. But what you can find by messing around with those laws is that you can have an alternative expression for the speed of light. And then the speed of light is actually 1 over the square root of those two constants that we've been dealing with, permeability of free space and permittivity of free space. So that's pretty interesting too, right? that the speed of light didn't just come out of nowhere, or maybe we could say that those two constants, permeability and permittivity of free space, did not come out of nowhere. They're actually related to the speed of light. So this relationship might come up. You might need this to do some math. And that is what I have set for this set of lectures for chapter 22. There, I believe, will be one more lecture set. I know this one might have ran kind of long because I get excited about this stuff. So stay tuned for the next lecture set. Right, have a good day.